You clean the sink, you pour bleach down the drain, wait for the fizzing to stop, run hot water for a full minute. By the next morning, the smell is back. Faint at first, then unmistakable. Like something died just out of reach. It feels like the sink is broken. It isn't. The real explanation has nothing to do with dirty dishes and everything to do with an organism whose survival strategy is older than almost anything else on Earth. Your brain wants a simple story. Food goes down the drain. Food rots. Rot smells bad. That story is true, but it explains almost nothing about why the smell always comes back within a day or two, no matter how much you clean, and why bleach seems to work for exactly one night before failing completely. The bigger part of the story isn't sitting in your drain. It's growing on the walls of the pipe itself. Have you ever wondered why a drain can look completely clean and still smell terrible? It's because the smell was never coming from anything visible in the first place. It's coming from a thin, slimy layer coating the inside of the pipe, a layer so structurally organized that microbiologists gave it its own name, biofilm. Biofilm isn't just bacteria sitting on a surface. It's bacteria that have built themselves a shared shelter, individual microorganisms attached to the pipe wall and secrete a sticky matrix of sugars and proteins around themselves, gluing together into a single cooperative structure that can be dozens of layers thick. Microbiologist Bill Costerton, whose research helped establish biofilm as a distinct field of study, described these communities as functioning almost like a fortified city, one where bacteria near the surface interact with water and oxygen, while bacteria buried deeper live in a completely different chemical environment, protected by everything layered on top of them. That layered structure is exactly why a quick rinse never solves the problem. Water and cleaning agents can wipe away the outermost layer of a biofilm, the same way wiping a countertop removes visible ants, but leaves a colony intact behind the wall. The layers underneath remain undisturbed, sheltered by the very structure the surface layer was built to protect. Within a day, sometimes less, the surface regrows because the deeper colony was never actually gone. Bleach in particular runs into a specific limitation here. As a chemical disinfectant, it works primarily on contact, killing whatever it directly touches. But the matrix a biofilm secretes around itself is specifically built to resist exactly that kind of penetration, slowing the diffusion of chemicals before they ever reach the deeper, more established layers. Pour bleach down a drain, and you're effectively disinfecting the outer few layers of a structure that might be dozens of layers deep, leaving the vast majority of the colony completely undisturbed beneath the surface you just cleaned. Here's the part that reframes everything. Your kitchen and bathroom drains aren't an empty pipe with occasional debris passing through. They're one of the most stable, nutrient-rich, undisturbed microbial habitats in your entire home. Ecologist Noah Fearer, who studies the microbiomes of everyday indoor environments, led research examining the bacterial communities living inside kitchen drains specifically, and found something remarkable. Drains host distinct, thriving microbial ecosystems, different in composition from the bacteria found on countertops, doorknobs, or even human skin. Constant moisture, a steady trickle of organic material, almost no direct light, minimal physical disturbance beyond the occasional rush of water. To a bacterial community built around exploiting exactly those conditions, your drain isn't hostile territory. It's close to ideal. Think about how different that environment is from almost anywhere else in your home. Your countertop gets wiped, dried, and exposed to open air and sunlight throughout the day. Your drain experiences none of that. It stays damp around the clock, receives a steady supply of food scraps, soap residue, and skin cells washed down with every use, and sits largely undisturbed in the dark for hours between uses. From a bacterial colony's perspective, that's not a harsh, hostile pipe. It's closer to a perfectly climate-controlled apartment with room service, delivered every single time someone runs the tap. This is also why the smell tends to concentrate in specific drains, rather than appearing everywhere at once. A bathroom sink, used only for hand washing, offers far less organic material than a kitchen sink handling food residue multiple times a day, so the biofilm colonizing each pipe develops at different rates entirely. The kitchen sink, statistically, tends to host the largest and most active community, simply because it's fed the most consistently. So why does it smell specifically like rotten eggs, rather than just generically unpleasant? That specificity comes down to one particular group of residents inside the biofilm, sulfur-reducing bacteria. Deep inside a biofilm, oxygen becomes scarce, blocked out by the layers above. Certain bacteria have evolved to thrive precisely in that low oxygen environment, and instead of breathing oxygen the way most familiar organisms do, they use produce sulfur compounds in their metabolism instead. The waste product of that process is hydrogen sulfide gas, the same compound responsible for the distinct rotten egg smell you associate with a bad drain. It isn't randomly foul. It's a precise chemical byproduct of a very specific survival strategy happening continuously, just out of sight, every single day. There's a second, entirely separate reason your drain might smell, one that has nothing to do with biofilm or bacteria at all, and it comes down to simple physics rather than biology. Beneath every sink and behind every toilet, there's a curved section of pipe holding a small reservoir of standing water, called a trap. That water isn't sitting there by accident. It's functioning as a physical seal, blocking sewer gas from rising up through the pipe and into your home. This design isn't new. Inventor Alexander Cumming patented the S-trap in 1775, specifically to solve the problem of sewage odor drifting back up through toilet pipes into living spaces, a design principle so effective that it's still the basis for every drain trap installed today, just refined into the curved P-trap shape used in modern plumbing. If a drain goes unused for even a week or two, perhaps a guest bathroom, a basement floor drain, or a rarely used laundry sink, that trapped water can slowly evaporate. Once the water seal drops low enough, there's nothing left blocking the connection to the sewer system beneath your house, and gas can rise directly up through the pipe with nothing filtering it at all. In that case, no amount of surface cleaning will help because the smell was never coming from anything living in the pipe. It was coming from an empty physical barrier that quietly failed. This distinction matters more than it might seem. A biofilm problem is a biological one, solved by physically disrupting a living structure. A dry trap problem is a mechanical one, solved simply by adding water back into a bend of pipe. Confuse the two, and you can spend weeks scrubbing a drain, replacing a P-trap, or pouring in commercial cleaners without ever addressing the actual failure. A basement floor drain that hasn't seen water in months doesn't need bleach. It needs a bucket poured directly into it, refilling the seal that evaporated away, and the smell can disappear within minutes once that seal is restored. This is why the same symptom, a smelly drain, can have two almost entirely unrelated causes: an actively growing biofilm colony producing sulfur compounds, or an empty water trap that stopped blocking sewer gas months ago. Solving one does absolutely nothing for the other, which is exactly why so many people feel like they've tried everything and the smell keeps winning anyway. Now here's the part that reframes the entire situation. Biofilms aren't some strange modern inconvenience created by plumbing. They represent one of the oldest, most successful survival strategies life on Earth has ever produced. Fossilized structures called stromatolites, layered mineral formations built by ancient bacterial communities, functioning almost exactly like a biofilm, have been dated to roughly 3.5 billion years old. That means the fundamental strategy sitting quietly in your drain right now, cooperative bacteria building a shared protective structure, predates animals, predates plants, predates complex life of almost any kind. It was one of the very first solutions life ever developed for surviving in a harsh, unstable environment, refined for billions of years before there was ever a pipe, a sink, or a house to grow inside of. Your drain is not a challenge to that system. It's simply the newest surface a multi-billion-year-old survival strategy has ever needed to colonize, and it adapted to that surface almost instantly because the fundamentals never changed. Find moisture, find organic material, build a shared structure thick enough to protect the community living inside it. So what actually works if bleach only ever provides a temporary fix? The answer lies in physically disrupting the structure the biofilm depends on, rather than simply poisoning its surface. Mechanical brushing, using a drain brush or snake to physically scrape the pipe walls, breaks apart the protective matrix directly, rather than relying on a chemical to soak through layers it usually can't fully penetrate. Hot water flushed regularly helps prevent the buildup of organic material the colony depends on to expand in the first place. And for drains that go unused for long stretches, simply running water through them periodically keeps the physical trap filled, preventing the sewer gas problem entirely, independent of whatever biofilm might also be present. Neither fix works well alone if you're dealing with both problems at once, which is why so many single-step solutions leave people frustrated. Address the biological structure and the physical seal separately, and the smell that seemed impossible to solve usually resolves within days. Here's the part worth sitting with. Every time you've poured bleach down a smelly drain and felt briefly victorious before the smell crept back the next morning, you were treating the visible surface of a structure engineered, quite literally, over billions of years of evolutionary refinement to survive exactly that kind of disruption. The colony living in your pipe isn't malfunctioning. It's succeeding, using a strategy so ancient it was already thriving before the first plant ever grew, before the first animal ever breathed, quietly rebuilding itself in the dark, one layer at a time, using nothing more than moisture, organic scraps, and time. So the next time you clean a drain and the smell fades for a night before returning, remember what's actually happening happening underneath. You didn't fail to clean it properly. You briefly interrupted the surface of a structure whose fundamental design has already outlasted nearly every other form of life that has ever existed on Earth. And it was always going to rebuild, because rebuilding, quietly, patiently, in complete darkness, is the oldest trick life has ever known.